Hi everybody, I'm Nikola and I will be teaching AP Biology, AP Calculus, AP Physics C, and AP Computer Science A. So officially I have 1 year tutoring experience in my senior year of high school with all the subjects mentioned above, as well as many more subjects. However, my personal learning process is teaching other students so that I can reinforce the ideas myself. So I like to believe that my tutoring experience extends throughout my whole academic career. Furthermore, I recently had a TA job, a teaching assistant at the Cooper Union, my current college, for a digital logic design class where I lectured 90 plus minutes to over 40 students about digital logic design, as well as had hands-on work one-to-one with each of the students, reinforcing the topics to them and essentially tutoring them. In addition to my tutoring experience, in my senior year of high school, I was awarded the Bausch and Lomb Honorary Science Award, and in applying to my current college, the Cooper Union, I was awarded the half tuition scholarship as well as the Innovators Merit Scholarship. So one of the subjects I'm most passionate about is electricity and magnetism, which is why I chose to tutor AP Physics C. Now, to get into an example of what a tutoring session of this subject would be, I'm going to show something a bit into the program about a derivation of the equation of an electric field inside and outside a charged insulated sphere. So let's get into it. Here's a charged insulated sphere. Say it has charge plus Q. All right. So from previous lessons, you would have learned that classic electric field from a point charge is E equal to KQ over R squared, R being the distance from the center of your point charge. Now, if we imagine this sphere has a radius of capital R and our arbitrary radius of anywhere inside or outside the sphere is represented by lowercase r. Outside of the sphere, from our lessons with Gauss's law, we know that electric field is directly proportional to the amount of charge enclosed by any Gaussian surface. All right, closed. So electric field is directly proportional to the amount of charge enclosed. So if we're outside of the sphere, we can imagine a Gaussian surface around it, and thus the electric field is only due to everything in the sphere. We can imagine it as a point charge, and we can say that when R is greater than capital R, the electric field is KQ over R squared. All right, so I'm going to box this together. When R is greater than capital R, this is the case. Now, things get trickier when we go inside the sphere. Insulating sphere, we're going to say it has a charge density of rho. Now, if remembering Gauss's law, we know that the electric field is only due to the charge enclosed at a given point. So we erase this Gaussian sphere from before. Now we're inside the sphere. We can deal with where R is less than capital R. If we imagine a Gaussian surface inside the sphere at this point R, the Q enclosed is only a part of the charge inside the sphere. So now, first we have to figure out what ratio, the amount of charge that is in this Gaussian surface. So if we begin, it's going to be Q times the ratio of the volume of the Gaussian surface and the volume of the entire insulating sphere. Now, so that'll actually be rho times that. So if we start, the volume of the sphere is 4/3 pi r cubed, right? Yeah, 4/3 pi r cubed. And if we find the ratio between the Gaussian surface and the total insulating sphere, we see that is 4/3 pi capital R cubed. So the volume ratio of the Gaussian surface to the total sphere is this. Cancel out the pi's and the 4/3. What we get is R cubed over R cubed. Okay, that's the ratio of the volumes. And essentially we're trying to make a similar expression to this. So the total charge is this ratio of volumes times the charge density. Charge density rho is in coulombs per meter cubed. So if we multiply rho by meters cubed, which is what this value is, we'll have coulombs, which is the amount of charge. So rho times that gets our q part of it. Put our k in the equation too. Over r squared, E is equal to that. That is the expression for the electric field inside the cube at an arbitrary r less than r. We can reduce this expression by crossing this out. And so the electric field is equal to k rho r over r capital R cubed. Now, quickly, before we finish it, we draw a graph of this. The electric field versus R, where this is capital R. The lowercase r is greater than capital R. We have a relationship of inverse r squared, which will look something like this. And for this one, we have a relationship that is linear, is directly proportional to r. So it will look like this. And that is the derivation for electric field around the insulating sphere. So I hope you enjoyed that little taste of my teaching style. A lot of the times when we're going to be in a tutor session, I'll do practice problems because I believe that's the best way to get yourself prepared for the exam and do well in your classes. Thank you so much for watching this video. I look forward to helping you in the future with your AP classes. For now, I'm Nikola.